Welcome to the third part of your first chapter. We had already finished in the first two parts. In the last class, we discussed about the three different structures, that is a simple cubic cell. And then after that, we also discussed body-centered cubic cell and then face-centered cubic cells. Now, here in this case, I'll be discussing about the first part will be what will be the relationship between the edge length, that is edge length for that particular cube, and the radius of the sphere. Now when I say sphere, constituent particle, it may be ions, atoms or molecule. So what will be the radius of that? Then the third one is what is the distance between the nearest neighbor. Okay, now look at this. This is the diagram that we took last week. The same diagram. The first diagram is for a simple cubic, or we call it as primitive cell. Second one is what is your body centered. The third one is what is face centered. Now I should tell you what relation are you going to derive. Now here you can see these are cut sphere. Now if I'm going for the first part, first one, uh, okay, let me use a yellow color. Here, this one is what is one cell. In fact, when I say one sphere, and this is another one. If I just show you two, this is the other one. Now, what is the radius? Now, if I'm wanting to find out the radius, this is what is the radius. I mean that is what is the radius of each of the sphere. Now, when I say sphere, let me represent it as atom. It can be ions and molecule also. So here, radius. Then, what am I talking about? The second one. The second one is what we call edge length. So, as you can see, this one is a cube. So, if this one is a cube, then in this cube, the side of the cube, here it is, edge of the cube, this one from here to here, this is what is represented by the symbol A. So that is what is edge length A. So from here to here, again I am repeating, from here to here, this is what is called edge length. Then the third one that will represent is what is called D. D means the distance between the nearest neighbor. Now two atoms which are very close to one another, you can see in this case the distance between the two nearest neighbor. So one is here. Okay, let me make it a little darker now. So one sphere is this one, and the other sphere is this one. Now what is the distance between the nearest sphere, nearest neighbor? Now, when I want to find out the distance between the nearest neighbor, then I have to take the center. Here it is. This is the center of the first sphere, center, and this is what is the center of the second sphere. Then, if I want to find the distance between the nearest neighbor, then this line which I am drawing from the center of the first sphere to the center of the second sphere, this distance is what we represent as D, which again I am repeating is what is D. This is what is D. So we are now going to derive what is the relationship between the edge length A, and second one is R. R means radius of the sphere, radius of the atom, and the third one is the distance between the nearest. Now we are going to discuss about these three in all the three cases, that is in the first simple cubic also, we are going to discuss that in body centered also, as well as also we are going to discuss in the third case, that is face centered. I repeat again. So what happens in your simple cubic, or what is the relationship between A, R and D in your body centered second diagram, and also what is the relationship in face centered cubic cell. That is what we are going to see. Alright, now that means now we are going to discuss the relationship between the three. Now as you saw the diagram, the relationship between how actually the different spheres are arranged in the three cases, but still better diagram is what we'll see. Now here, okay, I want to show you now, and then with the help of one video, I'll be putting it in the middle, how I'll be showing you how actually this came. Now here it is, one sphere, the radius of the sphere is R. Edge length you can see is A, and distance, what is the distance? Nearest neighbor. So as one sphere here, center is here, the other sphere center is here. So the distance from here to here, this red line that you see is what is D. Okay, I'm coming to that relation. Same thing here. In case of a body center, you can see in the center there is a big sphere, and 8 spheres already on the 8 corners. So now if you want to find out what is the relationship between A is here, the edge length, then R is this one, and the nearest neighbor distance in case of this one will be the center of this sphere. Okay, as I consider this one as one sphere, and the second sphere is that something is in the middle, they are the nearest neighbor, this red mark, and the distance between this nearest neighbor here, now I'm going to mark this distance, and the distance between the nearest neighbor is the center of this sphere to the center of this sphere. This is what is D. So this is what is a representation of your D. So this is what will be D here. D is this one. Again I am repeating, this is A. As you can see, this is A. This is what is R. And this is what is D. I'm going to show now again in the video how actually the calculation is done. Now you can also see here the relationship between actually, yeah, A and R. Here also, what is the relationship between A and R in the case of the first one also you can see. And in the third one, face centered, you can see this. Now I'll just show you where they are. Where you find the nearest neighbor. Okay, I think here I'll go with this one. If I'm considering this as one sphere, now you can see all spheres are there at the faces. This as another one, and the third one is the one which is there at the face. You can see here, third one, and they are touching each other. You can see they are touching each other. Now, if I want to find what is A, here is A. This is A, and what is R? R is already there. You can see represented as R. Then what is D? D is the distance between the, again I am repeating, it is the distance between the center of the nearest neighbors. So now if I am considering this one as the first sphere, this one middle of the first sphere, and this one is the middle of the second sphere, then the distance between these two center is what is representation as D. D is, again I am repeating, the distance between the two nearest neighbor. Now, so this is D, this is A, and this one is what is here R. So we are going to see now in these three cases what exactly are the.
If you want to find out the relationship between the atomic radius, if I am taking that atomic radius as R, the edge length of that cube, and if we are taking that edge length as A, and D, D standing for the distance between the nearest sphere. Okay, so now we'll divide our unit cell into three parts. The first one is the simple cubic cell. The second one is BCC, that is your body centered cubic cell, and the last one is what is FCC, or face centered cubic cell. Now in case of your simple cubic structure, now see what exactly happens. So in that case, we have our cube. Now if I try to make a cube here, if you have our cube here like this, then you know that in a simple cubic our spheres are located at the 8 corners. Okay, if I am talking about this one corner, this is another corner. Now the two spheres are touching each other. Now if I am taking the edge length of this cube as A, this one is what is A, and if I am taking the radius of each of the sphere, this sphere radius if I am taking as R, then see what is the relationship between R and A. Now since edge length is A, and A is from this center of this sphere to the center of this sphere, that is what is A, and that A is what is equal to radius of this sphere R and radius of this sphere R, so that is what is equal to 2R. Then the relationship between the edge length and R is that edge length is equal to twice of R, or in another term you can say that R is what is equal to A by 2. Then what is the distance between the nearest neighbor? Since these two cube spheres, one sphere here, the other sphere, are the nearest neighbor, and they are touching each other, even though in the diagram there is a small gap, they are touching each other, and the nearest distance is the distance between the center of these two spheres. So since the center of this sphere is here and the center of this sphere is here, now as the nearest distance between these two is from here to here, which is what is D, and that D is exactly equal to A. That means the distance between the nearest neighbor is same as the edge length. This is what is for simple cubic cell. Now if this is the simple cubic cell, now let us see what happens for the next one, body centered cubic cell. Now again I am repeating, see what is the relation now. So in case of simple cubic cell, your D is equal to A, that is distance between the nearest neighbor is same as the edge length, and the radius of each of the sphere, this sphere, the constituent particle, it may be atoms, ions or molecule, that radius of this one is what is always equal to half of the edge length, or you can also say R is equal to D by 2, because since A and D are equal, so that's why you can say that R is also equal to D by 2. Now going on to the second kind, that is body centered cubic cell. Now for that, let me erase this off. So let's see in a body centered actually what happens. So in addition to the 8 cubes which will be touching each other, here you are, this is what is your 8 cubes at the 8 corners. Here also there is also one cube which is there at the center. Here it is in the center. Now in this case, now what happens is, now if you want to find out what is the relationship between r, that is the radius of each of this cube, then d, the distance between the nearest neighbor, and a standing for the edge length. Okay, now for that what we need to do is, we need to first find out what is the distance between this cube here to this cube. Let me mark it with this one. Okay, let's see. So what is the distance from here to here? Let's calculate that. Now to calculate this distance, now what we'll do, we'll find out what exactly is the value of this. This is what is a, as you can see, this is what is the edge length a. This is also the edge length, so this is also a. Now this happens to be the hypotenuse. In this right angle triangle, this happens to be the hypotenuse. Now I'll take this hypotenuse as b. Now let me calculate first what is b. So hypotenuse square is equal to perpendicular square plus base square. So then I can say that b is what is equal to a square plus a square. So that is what is 2a square. So then 2a square under the root. So b is what is equal to root 2a. So now we know this b, this part which is b, the hypotenuse of this side, is what I'll take it as root 2b. Then after that, now what I need now is, if I want to calculate what is the relationship between d and r. Now next part that I'll move on now is now this relation. Now I need to find out what is the distance between this sphere to that sphere going through this middle sphere, Now if I want to find the distance from here to there, now what that distance is. So that distance again, if I want to calculate, then I need to take this right angle triangle. This is the right angle triangle at which I am going to take now. Here it is. That is equal to, so if I am marking this one as c, so suppose this distance, if I am marking it as c, then if I want to find c, hypotenuse is equal to perpendicular square plus base square. Don't forget, here one is this a, this is what is base, and the other one is what is this one. So this distance is what I am calculating. So that is what is equal to b square. Then this c square equal to a, this is a square plus b is there upper side. We have already calculated what is b square, and b square is what is 2a square. So c is equal to root of 3a. So now we know that c is what is equal to root of 3a. And c is the distance from here to there, total distance, and that total distance is equal to, now let's see how many radius are present in that. Now if I want to find out the total radius which is present there, so then let's calculate now one by one. Here is one radius, one, this will be touching this one, so it will be this again another radius, 2 radius, this is 3 radius, this is 4 radius. So that means altogether 4 radius is what is making up c. So 4 radius is what is c. So again I am repeating, this is touching this is sphere. So this sphere will be touching this sphere, and even though in the diagram you can see they are separated, but you have to understand that these 2 spheres are touching and these 2 spheres are also touching. So then total distance is r plus r plus r plus r. So that is why 4r is what is equal to root 3a. Now this will give us a relationship between r and a. So r is what is equal to root 3a by 4. This is what is the relationship between r and the edge length. Now if you are talking of the distance, nearest distance, then the nearest distance between the 2 spheres is, I'll take this and this sphere. Okay, let me take another color now. Let me take this color. Now the nearest neighbor is this sphere in the middle and this sphere. These are the 2 spheres which are the nearest neighbor. Now if I want to find out the distance between these 2 nearest neighbors, then you can see that one is what is r, then the other one is also r, is what is equal to the distance between the 2 nearest neighbor. So then d is what is equal to r. or you can say r is what is equal to d by 2. This is what is the relationship between the nearest distance and r. Now going on to the face centered now. So by the way, here it is, the relationship between r and d is this one, and r and a is this one. So this is for your body centered cubic cell. So body centered there in the middle. Now for that, so this is how we do the calculation. Now going on to the next one now, face centered. Now I need to erase this off first. So if I erase this off, okay, here we go. Okay, now for a face centered, okay, let me make a diagram. So here I am making a cube again, like in the previous case. Here again, in addition to the 8 cubes. Okay, now let me make those 8 cubes. Let me take the help of this red one. So sorry, not 8 cubes, 8 spheres. So one here, second one here, third here, fourth here, fifth here, sixth here, seventh here, and 8th one here. Now in addition to this 8, now there are also in the 6 faces there will be 6 sphere. Okay, now let's talk about this upper face here, one, then second one here, then in this face also this. Now let's talk about only one face. Now if I am talking about one face, now to find out the relationship between r, then d and a. So where r is the radius of each of this sphere, d standing for the distance between the nearest neighbor, and a standing for the edge length. Then if I want to find out the relationship between the two, then I need to draw a line through this sphere till this sphere, going through the face center sphere. As you can see, this is what it is touching. In fact, these 3 spheres are touching each other. Now you have to understand that this sphere, this second sphere, and the third sphere, they are touching each other. Now this is what I'll consider it as B. So let's give a name to this line as B. Now if I want to find what this B is, then here using Pythagoras Theorem, hypotenuse, this B is what is your hypotenuse. So if that B is what is the hypotenuse, so then is equal to base, lower base, you can see this is what the base is, that is what is edge length A, and height, here it is perpendicular, is also A. So your B is equal to 2a square, then b square is that, so b is what is equal to root 2a. So that means now you know the total distance from here to there, from this sphere to this sphere. Again I am repeating, from this sphere to this sphere, the total distance is what is root 2a. Now let us see then how much is the total distance from here to there. Now if I want to calculate the total distance, okay, taking some other color, okay, let me take the green color. Now as these 3 spheres are touching, this sphere is touching this sphere, is touching this sphere, is touching that sphere. So the total r, let's calculate what is the total distance from here to there. This is r plus another r, third r, fourth r. So that means now I'll write that 4r is what is equal to b, because the total distance from here to there is what is b. Then r is what is equal to, or 4r is what is equal to b. Just now above there you found out what is b, and that is what is root 2a. So r value is what is equal to root 2a by 4. Now this is what is the relationship between radius and the edge length. I repeat again, r is what is equal to root 2a by 4. Or if you want, then you can also write down as what is the relationship between a and r. So if you cross multiply and find out, let me cross multiply. Root 2a is what is equal to 4r. So a is what is equal to 4r over root 2. If you rationalize this, so lower root 2, so upper side also multiply with root 2. So that is what is going to give you this is what is going to give you 4 root 2 r over 2. That also further, when you cancel this, 2 is cancelled with 4, 2. So a value is what is equal to 2 root 2 r. So that means this is what is the relationship between a and r. Now if you want to find what is the distance between the nearest neighbor, so nearest neighbor, again this 2 happens to be the nearest neighbor. So this is one, this is the other one. So nearest neighbor is d is equal to, we calculate here, d is equal to r plus r. Or in another term, now you can say that d is what is equal to 2r, or r is what is equal to d by 2. This is what is the relationship between radius and the distance between the nearest neighbor. This is what is the relationship between A and R. So this is how you do the calculation based on. Now let us see a question now. So now what type of question you may be getting in the exam to solve with respect to this kind. Alright, now let me tell you what exactly is that. So the question says, xenon crystallizes in a face-centered cubic lattice and the edge of the unit cell is 620 picometer. What is the nearest neighbor distance and what is the radius of xenon atom? Right, now first let me write down what is given to you. It is written that the face centered, it is face centered, and the edge length and the edge of the unit cell. So edge, let me write down, A is given as 620 picometer, and it is already written face centered. Then we have discussed that the nearest neighbor in face centered D is what is equal to A by root 2. So D is what is equal to A by root 2. Now again I am repeating, this is what is the relationship between here A and D in a face centered cubic cell. Okay, now if that is so, then that is what is equal to 620 picometer divided by root 2. Root 2 value is 1.414. Now if you divide 620 by 1.414, that is what is going to give you 438.4 picometer. Same way, now the question, what is the nearest neighbor distance and what is the radius of xenon atom? Now radius is also asked. Now if you want to find the radius was something like this, A over 2 root 2. So this is what we already derived in a little while ago. So that is what is equal to 620 picometer divided by 2 into 1.414. Now if you do the calculation, this is what is going to give you 219.2 picometer. Likewise, now you may be asked question based on BCC, that is the body centered or a simple cubic. This relation that you have learned just now is what you have to use in order to find the values.
Okay, now let's see the close packing of sphere. Now, whenever a crystal is made, so you know different spheres, these balls which are there, atoms, ions, and molecules will be arranging themselves. Now, how will they arrange themselves? Now, in order to understand the three-dimensional packing, how the packing is done, packing means arrangement. First, need to understand what is two-dimensional packing. Then after that we'll go to three-dimensional packing. Now I think three-dimensional packing with the help of a diagram also here may not be very clear, but then again when you see an animation, then I think it will give you an idea about what that 3D packing is. Okay, before we go on to 3D packing, first let's see what is 2D packing. Now the sphere, atoms, constituent particle, atoms, ions, and molecules may be arranged in these two major forms. There are also other forms, but then these are the two major forms. Okay, now look at this, the first and the second one, what they are. In the first one, as you can see, there is an array of spheres here. These are all spheres. And similarly, in the second line also arrays of sphere. Then third arrays of sphere. Now, you can see if you are talking about any one sphere. Okay, let us talk about this sphere which is here. Okay, this sphere. I am talking about this sphere. This sphere is in contact with four more other sphere. Okay, what are the other sphere here? 1, 2, then 3 and 4. These are the four spheres which are in contact with this middle sphere. And don't forget, this sphere is not touching that, this sphere is not touching, this sphere is not touching, even this sphere is not touching. Now, if I join, by the way, this is what is called coordination number. Now, how many spheres are touching that main sphere, one single sphere? That's what is called coordination number. So, in this case, the coordination number is 4. Now, if I join the center of all the spheres which is touching this middle sphere, then it will come something like this. See, there 1, 2, then 3 and 4. Then you can see the shape which is coming out is coming in the form of a square. So that is why such kind of packing is what is called square packing. Even though we are here discussing only about two-dimensional, so this is what is square packing. Now again, why this name square is there is because of the center of the four sphere which is touching that main sphere, which is making of a square. Whereas the other kind of packing, as you can see, the second one which you see, is the kind where one particular sphere, by the way, now you can see the first line, the second line. Now the second line spheres are in the gap of the first line. Here they were not in the gap. In the first case, they were straight. The spheres were arranged straight. But here the second line is in the gap of the first line gap. Then similarly, the third line is in the gap of the second line. Now, if you take any one sphere, okay, let's talk about this sphere in the middle. It is being touched all around it by six different spheres, as you can see, numbered 1, 2, 3, 4, 5, 6. Now, if I join the center of all this sphere, 2, 3, then again here it is. If I am joining all of this, then you can see a hexagonal shape is what is coming out. So here 1, 2, 3, 4, 5, 6 is coming out. Since it is coming hexagon shape is coming, so such kind of packing is what is called hexagonal. So hexagonal packing. So hexagonal packing is what is this? By the way, this is 2D. We have understanding 2D so that we can understand that 3D packing better. Now, so that first one is what is called square packing, and the second one, as you can see, is what is called hexagonal close packing. So each particle is in contact with four other particles. You can see here in the first case, whereas in the second one it is in contact with six other particles. Now let's talk about two layers. So first diagram that you saw was only one layer. Let's suppose you have put some marbles on the floor as one single layer. But over that, now one more layer if you are putting on the top of that, then as you can see the first layer is hexagonal. Now as you can see, first line, second line is in the gap of the first line. Then again in the second layer, upper part of that one, if you put again one more set of marbles if you are putting, then this kind of arrangement is what is called here double layer. Now double layer is being followed by triple layer. Now one more layer over that. Now if you have then two major kind of arrangement of in this kind of arrangement is what we call a 3D packing or a three-dimensional three-layer packing. In this three-layer packing, you can see this is the first layer, this black color that you see as the first layer. Then the blue color ring that you see is in the gap, whatever was the gap in the first layer. So the second layer has gone into the gap of the first layer. Again, the third layer, which will come above that second layer, again will exactly coincide with the first layer. That means first layer and the third layer will be exactly coinciding with one another. So one will be above the other one. So again, I am repeating, first layer and third layer will be same, and similarly second layer B and the fourth layer will be same. So that is why such kind of packing is what is called AB packing. So as you can see, A first layer and this A, because they are coinciding. This layer and the third layer, they are exactly same. Whereas B, again one more B will come, the fourth layer which will be the B, and such kind of packing is what is called AB packing, or we call it as hexagonal close packing, HCP. Again, I am repeating as many times now, I may refer to it as HCP. Such kind of packing is what is called HCP, hexagonal close packing. Whereas now if you look at the other one, first layer, as you can see, hexagonal in the gap, the first layer, the second line is in the gap of the first one. Then the second layer which is there is coming into a gap of the first layer. But the third layer which is coming will be lying not exactly over the first layer, like in the previous case A and A, but the third layer also will be different from the first layer. That means it is different from the second layer as well as also different from the first layer. That is why all these three different layers which are there are all different from each other. No layer is coinciding with the next one. So because of that only, this layer or this kind of packing is what is called ABC or ACB packing, and this is also sometimes called as cubic close packing or CCP. So now two major 3D packing, one is HCP, hexagonal close packing, and the other one is CCP or cubic close packing, what we are going to see. Now the same representation in the form of ball, if you see, one is what is CCP and the other one is what is HCP. So if you can pause the video and see like how the arrangement of the balls in case of HCCP layers, first layer, second layer, three layers is what they are showing actually. So first layer, second layer, third layer coinciding. If first layer is coinciding with the third one and second is coinciding with the fourth one, then we call that as HCP. But none of the three layers are coinciding with each other, so all different layers, then we call that as CCP. Okay, the same thing again in another diagrammatic form. So here the first one is what is hexagonal close packing. So upper side is an animated part, lower part is same kind of ball is what is being shown. Hexagonal close packing and close cubic close packing, the second one. Yeah, now look at this. What I told you now, the first layer, which is as you can see, gray in color, and the third one is also gray. They are similar. The second one and third one, blue. So they are coinciding. That is why it is called AB kind of close packing. Whereas here, first and second and third, all of them are different. The first and the third, they are also not coinciding with each other. So that's why all three different colors is what they have used: blue color, gray color, and yellow. Again, the first one and the fourth one are coinciding first with the fourth one. That is why such kind of packing is what is called ABC close packing. Now we'll calculate now closing packing efficiency. Now what do we mean by packing efficiency? For example, if you have to go somewhere, now maybe after finishing class 12, we'll be going to the hostel, and maybe you're going out of your hometown. Then when you are going, you have to pack your bag with your clothes and all your belongings. Now you have to make sure that the bag that you are packing must be efficiently packed. It is not that it should be empty on one corner and then it should be fully packed on the other. Your bag should be as efficiently packed as possible. So the more efficiently you pack the bag, then that is what is called how efficiently have you utilized the space inside the bag. That is what is called packing efficiency. For example, if your bag is considered as 100%, and then your belongings 90% of your bag, if you have filled it with your belongings, then we say your packing efficiency or packing fraction is 90%. Same way, whenever a cubicle or your let's call it as unit cell is packed with spares, small space that you saw, it is not necessary that all 100% of that unit cell is covered with spare, because some portion of that is what will remain empty. So, what portion of a unit cell is filled with spares, the constituent particle, atoms, ions, and molecules, is what is called packing efficiency. Now, we'll see packing efficiency in case of your simple cubic, as well as also body centered, as well as also face centered. And don't forget, we discussed in the last class about the rank. In your simple cubic, rank is 1, total number of spare present is only 1. Whereas in case of your face centered, so we have rank of 4, total number of spare present is 4, and in case of your body centered, rank is 2. Rank 2 means total number of particle present is 2, because we require this one in order to calculate the packing. So let's see then, out of the three, which is the most efficiently packed in a simple cubic cell. Now for that we need a formula to calculate that. So then there it is. To find out the packing efficiency of any crystal or of any unit cell, volume of the sphere, I hope you still recollect the formula of volume of the sphere, which is 4 by 3 pi, the value of pi, we take it as 22 by 7, r cube, where r is standing for the radius of the, r is standing, and r is standing for the radius of the sphere. Divide by total volume of the cube. I hope again you also remember the volume of the cube. If cube has a edge of a, one side as a, then the volume of the cube is a cube. So this is what is the formula. So if you want to find packing efficiency, volume of the sphere, how many spares are present, that you will take it on the upper side, divide by total volume of the cube into 100, because we are expressing this in percentage, that's why we will multiply with 100. If you want to express in fraction, then you don't need this 100. This is what is the formula for calculating a packing fraction. So here it is, 4 by 3, you can see here 4 by 3 pi. Okay, please consider this as pi, even though it's not represented properly. R cube, R standing for the radius of the sphere, where A is standing for the edge length, A cube, because that is what is the volume of the cube, into 100. And now what is this n? This n stands for the number of such sphere present. As I told you just now, that a simple cubic n is 1, because only one sphere is present in a simple cubic. 8 corner, 1/8 into 8. Whereas in case of face center, this is 4. Whereas in case of your body center, this is 2. So depending upon whether it is you are calculating body center, simple cubic, or face center, this n will change. All let's see then the calculation. First we'll start with the simple cubic. Now in a simple cubic, again formula is the same. So the formula same copied. Now you know what is n. So n value is the number of sphere, and in a simple cubic or a cubic crystal, primitive cubic crystal, n is 1. Now if n is 1, there it is, n 1 into 4 by 3 pi r cube, pi will take it as 22 by 7, r cube, this r cube and this r cube, this lower side is 2 into 2 into 2, 8 r cube, this r cube and r cube, this r cube and r cube will get cancelled. So lower side you have 8. Then if you are taking pi value as 22 by 7, then that is what is going to give you the value as 52.4. So this 52.4 is what we call as the packing efficiency of a simple cubic cell. Now you should understand that if out of the total of 100, if 52.4% is packed with spares, then the remaining is empty, and that empty is what we'll call as, by the way, again I'm repeating, that empty space is what we call as voids. Okay, again I'm repeating, so that is what we call as voids. Now here, void, yeah, we call that as voids. Then how much is void? Okay, now going on to the next one, that is your body-centered cubic crystal. Body-centered, yeah, n value is 2, so replace that 1 with 2. That is the only difference now. So previously n was 1, now replace it with 2. Same, or rest of the formulas are same. Now your lower side is written 4 by 3 r cube. This is not 4 by 3 r cube, rather this is what is your we are discussing about the side of a cube, and that side of the cube is what is considered as 4 by 3 r cube, and that is what is going to give you a 68%. 68%. Yeah, this is what is 68. That means compared to just a simple cubic cell, this is a lot better. I would call it as a packing fraction as compared to this one, because that was only 52%, if I round it off. And this is what is 68%. That means packing efficiency in case of your body center is better, 68%. That means the remaining part is what is your 32% is what is void. Now, there is a small confusion with respect to this. Why previously we took the volume of the that unit cell as a cube. Now why are we taking 4 by 3 r cube? Previously, what is a? If you remember the relationship between a and r in terms of, or a and d in terms of the first video which I have put, a is equal to 2r. So that is why in the previous case we had taken it as 2r. So if you remember, lower side it was 2r, because we need to cancel this r upon r with the lower r. That's why you convert it in case of a simple cubic. A, instead of a's length, I took it as 2r, and 2r cube is what we had done. A cube was 2r cube. But then in body center we have already found that the relationship between a and r is that a is what is equal to 4 by 3 r. So that is why now instead of a cube, you can see instead of a cube we have written it as 4 by 3 r cube, because we need to cancel this r and r. If I keep here a, I'll get the a's volume, in fact volume of the cube, but then I need to cancel out r. That's why what we found out as a relationship between the a's length and the radius. So that was the relation. A is what is equal to 4 by 3 r, and that relation only is what we have used here, 4 by 3 r cube, and that is what is giving you 68%. Same way, if you go on to the next one, your face centered n value is what is 4, and yes, again here, why that 2 root 2? The relationship between r and a in face centered, a is equal to 2 root 2 r. So since this is a cube, so here this one is a cube, but instead of a we wrote 2 root 2 r, because we need to cancel out with the upper r. So that's why that a has been replaced with 2 root 2 r. So that is what is giving you 74%. So that means out of the three, the face centered efficiency is the best, 74%. Even the second one was only 68%. So whereas this is what is here 74. So that means void. So that means if 74 is efficiently packed, the remaining 26% is what is void. So that means out of the three, if you compare, the worst packing was the first one, that is simple cubic cell. Then comes your body centered, and the best packing fraction, as you can see, 74% is what is your centered cubic cell. Okay, so this is what is with respect to the body centered, and the first one 52%, this one was 60%, whereas in case of your face centered, it was 68 to 70, 74%. Okay, now we also need to discuss about what are different holes. Just now we discussed about the empty spaces. the voids. There are two kind of voids. By the way, here you can see holes. Holes are nothing actually but voids. We call them as voids. So two kind of voids are there. Voids means empty space, what is not occupied. So we call them as tetrahedral void and octahedral voids. Now what these tetrahedral and octahedral voids are? Okay, here when a tetrahedral void is formed, you can see three sphere, okay, see touching each other, forming a triangle, and one sphere kept in the second layer. So you can see this purple color sphere is in the second layer. And if you join the center of all the spheres, join the center of all these spheres with one another, if you join, then you know a tetrahedral structure is what comes out. Here you can see a yellow line which I made is what is a tetrahedral structure. That is why the void, the empty space which is there in the middle, is what is called tetrahedral void. Whereas here, six sphere, one kept over the other one. You can see the yellow one, the brown one, and the purple one overlapping with each other. So in the gap which is created in the middle is what is called here octahedral void. Now, next one is we will find out what is the relationship between the radius of the void. Now see, void is an empty space. So if it is an empty space, it is not spherical. But in this empty space, okay, by the way, let me use this blue color here. Now, if in this empty space, what is the biggest sphere that you can fit? And what is the radius? That radius of that sphere is what we call as small r. Now, we are going to find out what the relations between small r and capital R. And similarly, what is the radius of the sphere which is making up the void? If this one is the sphere, so what is the radius of the sphere which is making up the void? That radius is what will represent as capital R. Now we are going to find out the relationship between small r and capital R in a tetrahedral void and octahedral void. Again, I am repeating, what is small r? Small r is the radius of the sphere that would have fitted inside the void. There is no sphere, but what is the biggest sphere which can be fitted inside the void, in that void as well as also in this void? And what is capital R? Capital R is the radius of the sphere which are making the void. So you can see here in this as an answer, you can see already you can see is marked in a tetrahedral void. You know the relationship between capital R and small r is this 0.225, whereas in case of octahedral it is what is 0.414. Now how these two values are coming, now I am going to show you. Alright, now let us see in case of octahedral void, how do we calculate the relationship between capital R and small r. Okay, now here in octahedral void, this is how the arrangement is. Four spheres touching each other, and if these four spheres are touching each other, then you can see void. Here is the biggest sphere which can be fitted inside the empty space is this one. And let's suppose this sphere, small sphere, has a radius of small r. This bigger sphere is having the radius of capital R. Now, I am going to derive the relationship between capital R and small r. What is the relationship between the two? Now, to find the relationship between the two, okay, yeah, I am going to take this triangle. Okay, let me take this color. Okay, the triangle I am going to take is this one. Here, this triangle is what I am going to take. This triangle. Now, this triangle you can see has a side. This is what is A. This is also A. But don't forget A is equal to R because this radius is R, capital R. This is also capital R. So our edge A is what is equal to 2R. Okay, then.